In the realm of decentralized off-grid power, photovoltaic solar panels are the undisputed champions, estimated to account for 90 to 95% of all such energy solutions. Many consumers scarcely consider alternative options. However, wind power can be an incredibly beneficial complement to numerous self-sufficient energy systems. Today, discussions of wind power often conjure images of immense, 300-foot industrial turbines owned by colossal utility corporations. Home-scale wind is frequently dismissed as a mere hobbyist pursuit, while our attention is steered towards solar installations that demand substantial physical space and commit homeowners to a 20-year financial obligation. Yet, the fundamental physics of wind's energy potential should not be underestimated. A mere cubic yard of air moving at 20 miles per hour possesses a significantly greater energy density than the photons striking a solar panel of equivalent dimensions. I am about to introduce 6 exemplary turbines, representing the vanguard of off-grid wind technology, which you can integrate into your personal decentralized energy framework. Each is ingeniously designed to surmount the principal challenges inherent in small-scale wind energy generation. I will analyze each on the basis of its cost, operational efficiency, and what distinguishes these as some of the most groundbreaking projects in the current off-grid energy landscape. Our 6th featured innovation is the Tesseract Atlas. A major impediment to adopting home wind power is the requirement for a towering support structure. Many local building ordinances or homeowner associations perceive a 60-foot mast as an aesthetic blight or a violation of zoning regulations, serving as a subtle form of suppression. Without the ability to elevate a turbine sufficiently to access consistent high-velocity airflow, conventional setups prove impractical, leaving individuals tethered to the conventional grid. Fortunately, constructing an imposing tower is unnecessary if one reimagines the method of capturing wind. This is precisely where the Tesseract Atlas enters the picture. The Atlas is a vertical axis wind turbine meticulously engineered to circumvent stringent zoning restrictions and address the unique complexities of residential settings, all while maintaining realistic capital expenditures for home installations. In typical neighborhoods, structures such as houses, fences, and trees disrupt the flow of air, creating highly turbulent and unpredictable gusts. Standard horizontal wind turbine blades must constantly reorient their entire apparatus to face the wind, resulting in substantial efficiency losses each time the wind direction shifts. The Atlas, conversely, is indifferent to the wind's directionality. Its aluminum scoops are arranged vertically around a central axis, providing a 360-degree capture area. It harnesses kinetic energy from all directions concurrently, enabling it to perform optimally in the chaotic, swirling air currents found at roofline elevations. However, the true marvel of its engineering lies in its handling of structural forces, which translates directly into significant financial savings. When a conventional horizontal propeller-style turbine is affixed to a building, the uneven aerodynamic pressures generate considerable lateral sway, low-frequency vibrations, and dynamic oscillations that transmit into the building's structure. Rectifying these issues typically necessitates engaging a structural engineer and incurring thousands of dollars for structural reinforcement. The Atlas completely obviates these concerns. Because it rotates on a perfectly balanced vertical axis, all mechanical forces are directed straight downward through its center of gravity. There is no rhythmic buffeting, nor are there any low-frequency vibrations. Its operation is remarkably quiet, allowing it to be securely bolted directly to a standard roof beam or a simple ground-based pole. From a financial standpoint, this system fundamentally alters the economics of residential wind energy. A robust entry-level version of the Atlas Core generator commences at a very accessible $900. Complete modular kits, including custom blade profiles and advanced charge controllers, typically range between $1,500 and $3,000. In terms of power output, the Atlas Core features an integrated Internet of Things generator capable of producing an impressive 10 kilowatts of raw potential energy, managing daily electricity generation through its embedded controller. The unit begins its rotation at wind speeds as low as 9 miles per hour and can be outfitted with specialized low-wind blades that reduce this initiation speed to 7 miles per hour. By requiring no additional land, remaining invisible to neighbors, and incurring installation costs a fraction of those for commercial-scale architectural setups, it transforms a restrictive zoning issue into a highly attainable energy solution. It demonstrates that harvesting the wind's power does not necessitate a 60-foot tower or a second mortgage. It simply requires a more intelligent geometric design. Our fifth selection is the SD Wind Energy SD6. Observing most contemporary wind turbines reveals a surprising fragility. They depend on intricate wind sensors, electric motors to orient themselves into the wind, and sophisticated digital braking mechanisms to prevent disintegration during severe storms. In engineering, complexity is the ultimate adversary of self-reliance. If a vital electronic component fails during a blizzard, your power is lost, leaving you with little more than an exorbitant repair bill. The SD6, developed by SD Wind Energy in Scotland, stands in stark opposition to such delicate complexity. This 6-kilowatt powerhouse eschews computerized automation in favor of robust, passive mechanical engineering. While most conventional turbines are designed to face directly into the wind, the SD6 employs a reversed configuration, utilizing a downwind architecture where the wind traverses the tower before reaching the blades. Consequently, it requires no motorized tail vane or computer chip to detect the airflow. The inherent force of the wind naturally guides the turbine into its optimal orientation, functioning akin to a heavy-duty weather vane. However, its most significant engineering triumph lies in its storm resilience. During high-velocity gales, conventional turbines must engage emergency brakes and cease operation entirely to avert structural damage. The SD6, conversely, does not shut down. It incorporates a purely mechanical centrifugal force system known as the delta rotor. As wind speeds escalate, the resultant physical force causes the thermoplastic composite blades to automatically twist, altering their mechanical pitch. By pitching backward, they effectively dissipate excess wind energy, allowing the turbine to continue generating power safely even in extreme gales, while other systems are rendered inoperable. Financially, the SD6 represents a substantial investment. It is a formidable piece of utility-grade technology for your property. The turbine itself, combined with a heavy-duty $9,800 hydraulic monopole tower and professional concrete foundation pouring, brings the total installed cost within the $25,000 to $35,000 range. While this is a considerable sum, the reward is unparalleled energy density. Equipped with a massive 19-foot diameter rotor, the SD6 excels in locations with moderate average wind speeds of approximately 12 miles per hour, generating an astonishing 10,000 to 14,000 kilowatt hours of electricity annually. Considering the average household consumes roughly 10,600 kilowatt hours per year, this single unit possesses the capacity to completely eliminate your electricity bill. Furthermore, the absence of digital components dramatically impacts its long-term operational expenses. Free from sensor-laden electronics, the turbine is engineered for a 25-year lifespan without requiring major repairs, necessitating only a brief annual manual inspection and a standard bearing replacement every 5 to 7 years. It embodies heavy-duty, uncompromising engineering. Yet, once the concrete has cured and the tower is erected, it stands as a permanent guardian of your property, working tirelessly day and night and performing at its peak during winter storms when solar generation is impossible. Our next featured turbine is the Liam F1. Developed in 2014 by Dutch inventor Marinus Meermit. This design harnesses the principles of an Archimedes screw to resolve many persistent issues that have plagued small-scale wind projects for decades. In open rural areas, wind flows in a laminar pattern, the steady, unbroken air current that conventional propellers were designed to capture. However, the moment a propeller is introduced into an urban, suburban, or wooded environment, this smoothness disintegrates. Air currents rebound off buildings, trees, and roof lines, reaching the rotor in a chaotic, gusting stream that changes direction frequently. A horizontal axis propeller must pivot its entire body to track these shifting winds, and every degree of misalignment results in a loss of efficiency. This turbine, however, features a conical spiral design that can accept incoming air at angles up to 60 degrees off-axis without compromising performance. Furthermore, the cone itself automatically orients into the wind without the need for sensors or electric motors. Its ingenious geometry finds its own alignment through pure physics. The true engineering advantage emerges as the air interacts with the rotor. As the spiral captures the moving wind, it channels the air into its form, redirects it 90 degrees, and decelerates it to near stillness by the time it exits the rear of the rotor. The outcome is a turbine that operates significantly more quietly than conventional designs. A 3-blade propeller on a residential roof typically generates noise levels between 55 and 65 decibels, comparable to a running dishwasher. The Liam F1, however, operates below 45 decibels, quieter than a household refrigerator. Some residents have even reported standing directly beneath the operating rotor during strong winds and hearing nothing beyond the natural sound of the air's movement. Its clever geometry not only makes it quieter and more adaptable to unpredictable wind conditions, but also renders it exceptionally efficient at extracting kinetic energy. The manufacturer claims that the spiral design captures up to 80% of the theoretical maximum energy available in the wind, a metric known as the Betz limit. From a financial perspective, the Liam F1 occupies the higher end of the residential market. The 1.5 kilowatt turbine costs approximately $3,200, and a fully installed system, including the controller, dump load, mounting hardware, and wiring, typically falls between $5,000 and $7,000. Our third innovation addresses the two most common drawbacks of residential wind power: disruptive noise and the risk of bird collisions. Standard propeller-type turbines, known as horizontal axis wind turbines, feature blade tips that move at speeds 5 to 7 times that of the surrounding wind. This high-velocity slicing of the air creates a piercing, rhythmic whoosh that can propagate throughout a neighborhood. Flower turbines based in the Netherlands and the United States completely resolve this issue by employing a vertical axis design that more closely resembles an aerodynamic tulip than a conventional windmill. Because the curved aluminum blades loop vertically around a central shaft, they operate at a much lower tip-speed ratio. This design renders them virtually silent, producing only a low-frequency hum that is easily masked by ambient suburban sounds. One can stand directly beside one and engage in a normal conversation. However, the true engineering secret here extends beyond mere silence. It represents a direct departure from traditional aerodynamics concerning how these turbines interact in proximity to one another. Standard propellers generate a significant wake of highly turbulent, disrupted air behind them. If two conventional turbines are placed close together, the second turbine will experience a substantial drop in efficiency due to being ensnared in the chaotic wake of the first. Flower turbines, conversely, exploit the opposite effect, a fluid dynamics phenomenon known as the cluster effect. Positioning these turbines in close proximity actually enhances their individual performance by up to 20%. The swirling air shed by one turbine's rotation acts as a mechanical gear, actively propelling and accelerating the blades of its neighbor. This characteristic allows for the creation of a high-density, modular power garden within a compact backyard or across a flat commercial rooftop. They are also entirely safe for birds, as the vertical scoops form a clear, solid cylindrical silhouette when in motion. Wildlife perceives them as an obstacle to avoid rather than an invisible hazard of rapidly moving blade tips. Economically, flower turbines are structured as highly adaptable, modular consumer technology assets rather than demanding extensive capital investment. A small entry-level turbine stands approximately 3 feet tall and begins at around $1,400, making it ideal for charging small off-grid battery banks. Mid-range models, designed for residential rooftops, start around $4,500, while their larger commercial-grade vertical units can cost up to $9,500. The true financial benefit, however, lies in their exceptionally low activation threshold. While industrial turbines do not even begin to operate until wind speeds reach 7 or 8 miles per hour, flower turbines commence generating usable electricity at speeds as low as 2 miles per hour. Given that gentle breezes of 2 to 5 miles per hour are far more prevalent in urban environments than high-speed gales, these turbines continuously feed a trickle of power into your system throughout the day. By leveraging the cluster effect, an investment in a small arrangement of 3 or 4 mid-sized units does not merely increase power output linearly. It establishes an interconnected, highly efficient microgrid that maximizes electrical generation from even the most confined residential footprints. Our second selection, Primus Wind Power, demonstrates that true innovation sometimes lies not in creating a novel form, but in the relentless refinement of a proven concept. Primus Wind Power, based in Colorado, manufactures the Air series of turbines, which are compact, microscale machines rated at 400 watts. To those accustomed to the vast scale of the centralized commercial grid, 400 watts might seem insignificant. However, Understanding baseline energy requirements fundamentally alters this perspective. A 400-watt turbine operating consistently through a dark, windy night provides the essential continuous power needed to operate an energy refrigeration, powering LED lighting systems, and ensuring critical communication networks remain functional when solar panel cells are completely ineffective. The Air Series was originally engineered for the demanding maritime industry, meaning its structural design was conceived from the ground up to withstand corrosive salt spray, sub-zero ocean winds, and the constant structural vibrations experienced on a sailboat's mast. Its casing is cast from aircraft-grade aluminum, and its specialized blades are molded from a carbon fiber-reinforced composite, designed to flex rather than fracture under significant aerodynamic stress. Mechanically, the system embodies extreme simplicity. The sole moving component of the entire machine is the rotor itself. However, the truly revolutionary aspect of its engineering is the integrated internal regulator. Historically, installing small-scale wind power systems necessitated a complex cabinet-sized array of supplementary electronics, including external rectifiers, dump loads, and heavy-duty charge controllers, solely to safely manage battery charging without damaging the system. The Primus engineering team miniaturized all of this infrastructure, embedding the electronic intelligence directly within the rotating nacelle of the turbine. This eliminates the need for an electrical engineering degree for installation. One simply connects two standard copper wires down the mounting pole, and they directly link to the battery bank. Financially, the Primus Air Series represents the ultimate entry-level pathway to wind energy independence. The complete, self-contained turbine unit typically costs between $1,200 and $1,500. And because it does not require complex external controller cabinets, your supplementary hardware expenses are virtually non-existent. In terms of actual energy output, the unit features an exceptionally low startup wind speed, with the carbon fiber blades beginning to rotate at just 7 miles per hour. Once the wind reaches a steady 12 miles per hour, a single unit will consistently generate approximately 30 to 35 kilowatt hours of electricity per month. It is the definitive plug-and-play microgenerator in the world of wind power. For a cabin, a mobile tiny home, or an emergency off-grid backup system, it offers a level of rugged, cost-effective simplicity that the multi-billion-dollar utility industry claims is unattainable. Our top-ranked turbine is the Icewind. This final turbine on our list addresses the challenge of excessive wind. In environments such as Iceland, the Great Plains, or high-altitude mountain ranges, the wind does not merely blow, it rages. Most residential turbines have a strict, vulnerable survival wind speed limit. If a storm approaches and wind speeds reach 100 miles per hour, conventional blades are susceptible to catastrophic structural failure and complete destruction. The Icewind turbine, engineered by an innovative design team in Iceland, subverts this limitation by creating a vertical axis machine specifically designed to thrive in these otherwise inhospitable conditions. The secret to its engineering lies in its highly sophisticated dual-blade configuration. The core of the machine features an inner Savonius-style rotor, which functions like a series of robust scoops, delivering substantial mechanical torque and enabling the system to activate and begin rotating even in extremely low winds. Encasing this core is an outer aerodynamic Darius-style blade system that takes over at higher speeds to maximize aerodynamic efficiency. By integrating these two distinct aerodynamic profiles, the ice wind avoids the typical structural stresses experienced by horizontal propellers. It is constructed from marine-grade stainless steel, aircraft aluminum, and carbon fiber, enabling it to withstand relentless, punishing wind speeds of up to 130 miles per hour without deforming or fracturing. Furthermore, its physical architecture is entirely sealed. Traditional windmills house their sensitive gearboxes and electronics high above ground, exposing them to freezing rain and dust. The ice wind places its heavy direct drive generator at the base of the unit, fully enclosed and protected from the elements. There are no exposed gears, no external wiring, and no mechanical micro switches prone to freezing. It operates as a silent, indestructible monolith, continuously converting kinetic energy into electricity under conditions that would shatter a conventional windmill. From an economic standpoint, the ice wind is positioned as a premium asset for extreme weather conditions. The residential and off-grid models, such as the Freya series, generally range between $3,200 and an undisclosed higher figure, depending on the specific generator output configuration. While it generates a modest 150 to 300 watts of continuous power, depending on the model's scale, the financial calculation here is not based on sheer volume, but on absolute dependability. Because the generator is direct drive and lacks a complex mechanical transmission, it boasts an exceptional 25-year operational lifespan with virtually no maintenance requirements. It needs no annual greasing, no electronic recalibration, and can be mounted directly onto an existing pole, a concrete pad, or a remote telecommunications tower. It is the ultimate set-it-and-forget-it energy solution for the planet's most rugged environments. It proves that when nature unleashes its worst, there is no need to shut down your system. You simply need technology robust enough to endure. While the entire world is rushing to cover their rooftops with solar panels, many individuals seeking energy independence overlook a fundamental principle of physics. Wind possesses a vastly superior kinetic energy density compared to solar power. Solar energy relies on capturing transient photons across a flat surface, whereas wind represents a three-dimensional volume of moving force. A single compact turbine operating through a dark winter storm can generate more raw energy in 24 hours than an entire residential solar array might produce in a week. If your objective is true energy independence, wind is not merely an alternative. It is the ultimate equalizer. However, achieving this independence necessitates moving beyond guesswork and grounding your setup in practical data. Your initial, definitive step is to quantify the invisible resource present above your head. Accurate wind speed measurement is not a matter of estimation. Investing less than $100 in a digital data logging anemometer and installing it at your intended deployment height transforms the entire decision-making process. By leaving the anemometer in place to record data for 6 to 12 months, you will accurately map your property's specific wind seasonality. If the collected data reveals an average annual wind speed below 8 or 9 miles per hour, wind generation may not be the most effective primary energy source for your location. However, if your local wind speeds are substantial, the financial viability of your complete energy framework undergoes a transformation. This is precisely where wind demonstrates its unparalleled advantage, serving as the ideal complementary force to solar power. During the harsh depths of winter, when the sun remains low on the horizon, daylight hours are limited, and solar panels operate at their lowest efficiency. Prevailing global wind patterns generally reach their peak intensity. By incorporating a solution such as the Primus Air or a collection of flower turbines into an established off-grid solar setup, you can significantly decrease your reliance on costly chemical battery storage by as much as 40%. Rather than investing thousands of dollars in additional lithium batteries to stockpile energy for periods of reduced generation, you are effectively allowing the wind to seamlessly bridge these gaps in real time, performing the vital task during nighttime hours while your solar arrays are inactive. Furthermore, the necessity of constructing massive, industrial-scale towers to achieve this is eliminated. Whether you opt for the all-encompassing urban design of the TESUP Atlas to navigate restrictive zoning regulations or deploy a robust unit like the SD6, engineered to withstand extreme open terrain winds, contemporary engineering has successfully miniaturized wind power technology to a more accessible scale. These innovative systems transform rigid local construction ordinances from obstacles into manageable design considerations. Wind itself was the very initial, cost-free energy source that humankind utilized to traverse immense oceanic expanses and process grains. It remains an ever-present resource. The staggering 200 trillion kilowatts of kinetic energy constantly circulating within our planet's atmosphere pass over your dwelling every 24 hours entirely without monetary cost. Should you subscribe to the notion that the air above your property represents a valuable resource rather than an inconvenience, and if your objective is to cease being dependent on a centralized utility provider for your energy needs, then the technology required to capture this aerial energy is now within your grasp. If your interest lies in attaining self-sufficiency in energy provision, and you wish to explore other avenues to achieve this goal, you might also find our video on Pico Hydro compelling. It details an inexhaustible energy source that you can construct yourself for a mere $50.